Hello and welcome to our new playlist of full tutorials on elective mathematics. In this particular tutorials, we're going to solve questions on sets. We'll cover all kinds of set problems you should be expecting on the WASI paper. And this is actually the first part of the video. I might actually bring another video to basically cover the rest. So without saying much, let's get right into it. So basically, a set is usually represented by a capital letter, a set, and it is described by elements within two curly braces. So this is a set P, and it could contain anything. So in this situation, this could contain 1, 2, 3, 4, 5. So this is called the set P, and the numbers we see inside here, 1, 2, 3, 4, 5, are the elements or the members of the set. Okay, so basically this is how sets are represented. All right. Okay, now the question we have at hand is that P is equal to 1, 2, 4, 5, and 7, and Q is equal to 3, 4, 7, 8. Are subsets of U, which is equal to 1, 2, 3, 4, all the way to 10. Find 1 P intersection Q, 2 P union Q, and 3 P complement intersection Q complement, and 4 P union Q or complement. I'll be explaining all these different notations as we go along. Okay, so the question says P is equal to the set 1, 2, 4, 5, and 7, and Q is equal to the set 3, 4, 7, and 8. And these two sets are subsets of the universal set U, which has these elements. When we say a particular set is a subset of another, it means the whole entire, all the elements within that particular set can be found in the set within which is a subset of. Similarly, all of the members of this set can be found in this particular set, which it is a subset of. So that's what they mean by subset. So we can see that 1, 2, 4, 5, 7 are contained within 1 to 10. Similarly, 3, 4, 7, and 8 are contained within this. So the first part of the question says we should find P intersection Q. This means that we should find elements of P that are also within elements of Q, meaning the elements that are common in both P and Q. Alright, so this is equal to, we just look and then we write out all the elements between two curly braces. So 1 is not found in Q, so we ignore that. 2 is not also, but then 4 is, and then 7. So the elements of the set P intersection Q is equal to 4, 7, and then we close it off. And this is the set, so this gives I. So this basically means intersection. What is common between, what is common in both sets, P and Q. Now P union Q means that we should combine the two sets and then write out the resulting set. Whenever any element occurs in both, we only record it once. Remember, union, you combine the two sets, but any element that occurs in both, you only record it once. So P union Q will be 1, 2, 4, 5, 7, and 8. So this gives P union Q, because these elements are a combination of the set P and the set Q. The third part of the problem says P complement intersection Q complement. So first we have to determine what P complement is and what Q complement is. P complement is basically all of the elements within the universal set. All elements within the universal set that are not members of the set P. So P complement means not, think about it as not in P. So all elements that are not in P but within the universal set. Remember, you have to restrict yourself to the universal set, otherwise you would end up always mentioning elements that really you can even go into infinity. But this basically gives it the limit, right? Okay, so elements that are within the universal set but not in P are 1, 2 are inside the universal set, but 3 is not. So 3, 4 is, 5 also is, but 6 is not. 7 is, but then 8, 9, and 10 are complements of P. Similarly, Q complements all elements that are not found in Q but are within the universal set. So we have 1, 2, 5, 6, 9, and 10. So this gives P complement and Q complement. Now we are supposed to find P complement intersection Q complement. So we now look at these two sets, and then we determine which elements are common in both, and that gives us the final answer. So P complement intersection Q complement is equal to the sets. So we have 6 is common here, so it's 9 and 10. So this gives 6, 9, 10. Oops, sorry about that. Now I'm just going to free up some space here. And do the last one. It says P union Q. What did I just do? I just cleaned up that. So I'm just going to rewrite Q here. Q is 3, 4, 7, and 8. So I'm just going to solve IV right here. So P union Q complements, right? So first we find P union Q, but then we already did that, right? P union Q is equal to this: 1, 2, 4, 5, 7, and 8. Now we find the complement of that. The complement of that gives the set of all elements that are not present in this particular set but can be found within the universal set. So this gives 3, 6, 9, and 10. And this solves the first question. Remember to leave your questions and comments below. Okay, question number 2 says, if A is equal to 2, 3, 4, 5, and 10, B is equal to 1, 2, 3, 4, 5, 7, 8, 9, and 10. And C is equal to 3, 4, 5, 6, 7. Find 1, A intersection B intersection C. 2, A intersection B. 3, B intersection C. 4, A intersection C. 5, A intersection B union C. Now I'm going to be introducing a few stuff with this question. A intersection C. Well, it's going to be an introduction only if you don't know it yet. I'm pretty sure you all know it. I trust you guys. B intersection C. And we have, I think, VIII. A union B intersection B union C. Okay, so let's do our solution somewhere here, freeing up some space along the way. So first is A intersection B intersection C. This means we should write out the sets of elements that are common in A and that are common in A, B, and C. So we should be able to find the elements in all 3 sets. Alright? Okay, so let's start checking them. So we have 3. It actually starts off with 3. So we have 3, 4, 5, and that's it. 3, 4, and 5, and that's it. Okay. 2, A intersection B is equal to, so elements that are in A that are also in B. So we have 2, 3, 4, 5, and 10. So we see that all of the elements in A are in B. Alright, so we can see that A is a subset of B, and this is the symbol for subset. It's not exactly an E, it's a C, but then cross it, and that's the symbol for subset. You should just know that, although no one will ever ask you what that symbol means, but it'll be used. So 3, B intersection C. And I'm pretty sure you see what's going on here, so you probably can just do the rest. So we have 3, 4, 5, and 7. And IV, we have A intersection C gives 3, 4, 5. Alright, now for these ones, I'm going to have to free up some space to really get down to it and introduce those concepts I said I would. So we have to find A intersection B union C. First, we find B union C. What is in the bracket? That is, so we have B union C is given by, so combining sets B and C, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Alright. So this is set B union C. Now we find the set A intersection B union C. Basically, what is common between set A and set B union C, which is this whole entire set. So this gives 2 is there, 3, so it's 4, 5, and 10. So, and that's it. Now VI says A intersection B union A intersection C. So first we find the sets in the brackets first. So we have A intersection B. Well, we already did that, and that is 2, 3, 4, 5, and 10. And then we have A intersection C is equal to A intersection C is 3, 4, 5, and that's it. So now we find the union of this and that. So A intersection B union A intersection C is given by 2, 3, 4, 5, and 10. Now, and this is actually the answer. Now you'll see that this is the same as the previous answer. This, by the way, demonstrates a property known as the distributive property of intersection over union. So let me free up some space and explain it a little better so you can understand. All right, almost there. Just a little more. Okay. Now, whenever you have this A intersection B union C, you can actually distribute this over that, just like you expand brackets. So you see A intersection B, expanding it, you have A intersection B union A intersection C. A intersection C. This is the distributive property. This means that the intersection operator is distributive over the union operator U. This is important to understand, and they are always equal. I mean, these two are equal. I mean, of course, it's the same exact thing. We just expanded this to get that. Okay? All right. Now let's do the last two. So we have VII, A union B intersection C. Again, we find what is in the brackets first before we go on. So we have B intersection C is equal to B intersection C. So what is common between them? We have 3, 4, 5, and 7. And so A union B intersection C is equal to A union this. So this, combining A and this particular set, we have 2, 3, 4, 5, 7, and 10. And this is A union B intersection C. And the next one says A union B intersection B union C. Is that it? Just give me a moment. Rather, it's A union C. Made a mistake. A union C. Okay. So again, we find what's in the brackets first. So we have A union C. A union C is given by, combining A and C, we have 2, 3, 4, 5, 6, 7, and 10. And A union B is given by 1, 2, 3, 4, 5, 7, 8, 9, and 10. So it's basically the set B. So now finding the intersection of this means we write out the elements that are common in both this set and that set. So A union B intersection A union C is given by the intersections. So we have 2, 3, 4, 5, 7, and 10. And that's the answer to that. Now again, we see that this is actually the same as that. And like I said before, this is the distributive property, but this time the union operator is distributive over the intersection operator. So let me free up some space and then just make it a little clearer. So whenever we have A union B intersection C, this also means that we can expand this over that. So A union B separately, A union B intersection, so bringing this now, A union C. So A union C. So this, in this situation, the union operator is distributive over the intersection operator. Now the one we wrote before was A intersection B union C is given by A intersection B union A intersection C. This means the intersection operator is distributive over the union operator. And that's basically the distributive property. All right. Let's see more problems. Okay, so, sorry. Given that A is equal to 5, 10, 15, 20, and 25. B is equal to 5, 25, 125, 625. And union, meaning the whole entire sets we are under consideration, is A union B. It's a combination of these two. All right. So now we have to list the elements of A complement union B complement and A complement intersection B complement. And I'll actually just add, just for the purpose of illustration, A union B complement and A intersection B complement. All right. So the first one first, let us write out the universal set so that we can see it clearly. They said the universal set is the combination of both sets. So let's just combine them and see. We have 5, 10, 15, 20, 25, 1, 2, 5, and 6, 2, 5. So this is the universal set. So now we first want to determine what a complement is. A complement again is the list of all, the set of all elements that are not contained in A but can be found in the universal set. So they are not supposed to be in A, but they should be within the universal set. Okay, so anything that is not here but is here, that is what we're going to write. And that is actually the last two. So we have 1, 2, 5 and 6, 2, 5. Okay, so that's A complement. B complement is also the set of all elements that are not within the set B but can be found within the universal set. So we have 10, because 5 is there, 10, 15, 20. That's it. And we close it off. So that is A complement and B complement. Now we have to find A complement union B complement. So the two sets we just found, we combine them. And this gives the set 10, 15, 20, 125, and 625. And this is it. Alright? Okay. Now let us do the second one. Alright, so again we have to find a complement that is for the II. I mistakenly claimed the universal set, so I'm just going to rewrite it up here. So the universal set is 5, 10, 15, 20, 25, 125, and 625. So for II, again, A complement is 125 and 625. B complement is given by 10, 15, and 20. Okay, so this intersection, that's basically what can be found in both elements. Now we see that there is nothing. So A complement intersection B complement is a null set, and a null set can simply be represented as this, or we can also write it in this way. We just write an empty set, two curly braces with nothing in it. So you can either represent it in this way or this way, one of them. Alright? Okay. Moving on now. Okay, so now we need A union B. Man, I cleaned the universal set again, but what the heck. Alright, A union B complement. So first we find A union B, which is actually the universal set. So A union B is given by 5, 10, 15, 20, 25, 125, and 625. And the complement of that, watch closely. The complement of this, remember this is actually the universal set. The complement of that, meaning the elements that are here, that are within the set, and not found in the universal set. And remember that the universal set is the same exact thing. The question said universal set is A union B. So if we were to list it out, it will be the same exact, it will contain the same exact elements, like so. So what is what element is absent here, but present within the universal set. We see that it's nothing. So this gives the null set again. So this gives null set. And again, this can be written as simply an empty set. Now there's something important that has just come up. Remember when we found A complement intersection B complement, it also gave us the null set. This is known as De Morgan's law. De Morgan's law. Let me free up some space and just tell you a little more clearly how the De Morgan's law looks like. So De Morgan's law says that A complement intersection B complement is equal to A union B or complement. Remember the notation, the operator in both cases. The intersection A complement separately, intersection B complement separately is equal to A union B or complement. This is De Morgan's law. And by the way, the other way is also true, meaning A complement union B complement is also equal to A intersection B or complement. These are both De Morgan's law. Alright, and then the last two examples, the very last example we are going to solve is also an illustration of that. Alright, so again, the universal set is this. I just don't know why I keep cleaning that. 25 and 625. Now A intersection B, elements in A, in both A and B, that is, so we have 5, 25. So it's just 5 and 25, and we'll close it off like that. So, and now we have to find the complement of that. So what elements are inside this, but not inside that? I just said it the other way around. What elements are absent within the set, but can be found inside the universal set? You guessed it, so it's starting from 10, 15, 20, 125, and 625. Now if you recall, this was the same as when we solved this. This also gave 10, 15, 20, 125, and 625. And like I said before, this is De Morgan's law. So they are the De Morgan's law. And that does this particular problem. Okay. Now we have if P, Q, and R are subsets of the universal set. If P, Q, and R are subsets of the universal set U, which is equal to prime numbers less than 20. Okay. And P, I'll just write it down there. And P is equal to X such that X is between 1 and 10 inclusive. Q is equal to x is such that x is greater than 5 and r is equal to x such that x less than 7. Find again P union Q and P complement intersection R complement Q intersection R. So basically, anyway, let's just do these three. I'm pretty sure you understand it by now. I'm going to try to do it at the bottom here. So 1, P union Q, right? Now, of course, first we need to write out the universal set. So the universal set is the set of prime numbers less than 20. So what are prime numbers less than 20? We list them out. So you see that writing out the elements row like that isn't the only way of representing sets. You can actually describe the sets like this without having to list them out. So in this situation, you will have to list them out anyway before you can find these more easily. So what are the prime numbers less than 20? So we have 1, 2, 3, 5, 7, 11, 13, 17, and 19. By the way, what are prime numbers? Prime numbers are numbers that have only two factors that can only be divided by 1 and the number itself, right? To give a non-decimal number, to give another number without a remainder, that is. So 20 divided by 2 gives 10 without a remainder, and 2 is neither 1 nor 20 itself, so this is not a prime number. But if you take any of these numbers we've listed, say 7, can only be divided by itself to give a number that doesn't have any points, whatever, or by 1 to give 7 itself. These are primes. Okay. So now we have to find P union Q. And P is all values of x such that x is greater than or equal to 1 inclusive. So greater than or equal to means it includes 1, but less than or equal to 10. Right? So P is all values of x such that x is from 1 inclusive to 10 inclusive. So we have 1, but remember, the universal set contains only primes. So meaning this will also contain just primes. Very important. So we list them out: 1, 2, 3, 4 would have been within this range, but it is not in the universal set, so there's no way it can be in P, so we don't write 4. Then 5, 7. So basically we write out the elements here that satisfies this condition. The elements here that are from 1 to 10. So 7. And 7 is actually the last number. The next number is 11, which is greater than 10, so it doesn't. So we end here. So these are the elements in the set P. Alright. R. Sorry, Q first. All values, the set Q is the set of all values of x such that x is greater than 5. Again, x must be greater than 5. So from above 5, that is 6 onwards. But again, it must be prime because the universal set contains only prime numbers. So we look at the universal set and we take only elements that meet this condition here. Okay, So that's exactly what we are going to do. So we are going to write out all members of the universal set greater than 5. So we have 7, 11, 13, 17, and 19. And now we have R. R is the set of all values of x such that x is less than 7. So again, we write out all elements in the universal set less than 7. And that's straightforward. 1, 2, 3, and 5. So these are the elements. Alright? So now P union Q. The rest is trivial. P union Q basically means we combine P and Q. So P union Q gives 1, 2, 3, 5, 7, 11, 13, 17, and 19. That didn't come out right. So 7, 11, 13, 17, 19. And then I close it off. So that's P union Q. P complement intersection R complement. So first P complement. P complement is the set of elements within the universal set that are not inside the set P. So P is 1, 2, 3, 5, 7. Elements that are not in P, are elements above that actually. So we have from 11, 13, 17, and 19. And R complement is the set of all elements within the universal set that are not found within the set R. So R only contains 1, 2, 3, 5. So complement of that starts from 7 upwards. 17, 19. So now P complement intersection R complement will be elements that are common in both P complement and R in these two sets. Now if we look at it, this part. So we have 11, 13, 17, and 19. And that's P complement intersection R complement. I leave the other one to you. To try it out. Remember to leave your questions and comments below. Alright, now let us begin solving some set problems. Okay. So we're not going to actually solve them. We'll solve set problems in the next video. Today I'm just going to give you how sets can usually be represented. So sets are usually for WASI. They are always represented on a Venn diagram. And remember that there's usually a universal set U, which will contain all of the sets under consideration at a given particular time. All right. So whenever you are presented with a question, there will be a universal set within which you will be working, right? And it is usually represented with a rectangle like so, and then it is labeled this way, and then the number will be written like so inside these brackets. All right, let me just call it X. Okay, now and inside it we can have subsets. All right, if there are two subsets that have some commonalities, so for instance we say we have a set A and set B, they're represented with circles, overlapping circles in fact. So this particular circle represents the set A. Represents the set A. Alright? Represents the set A. This particular circle also represents all of the sets B. Now the overlapping area here, I'm just going to shade it. This is A intersection B. Alright? Very important. Okay. So now, so you'll find that the area outside of the overlapping area. So let me use this. The area that has the dots, right, will basically be elements that are only within A or B. Basically, you don't find those elements inside A intersection B. Alright? Okay. So just a couple of things to note. So let's say we want to show we've already shown A intersection B, A union B, A union B complement, A intersection B complement, and let's see, A complement intersection B complement, A complement union B complement, and okay, let's see what we can do here. Alright, let's work with these for now. So let's say we want to illustrate these on a Venn diagram. See, so I'm just going to clean this up. Alright. If you already know this stuff, you can just skip to the next video. I want to really explain how the how information is represented on the Venn diagram. So again, we have the diagram, and of course this is the universal set U. And say we have A, the set A, and the set B, assuming there's some overlapping parts. Okay, so we are to shade the region A union B. So that means we are combining set A, all of set A, with set B, and that's all. So you find that the whole of this area, together with the overlapping area and the whole of the B, the whole of the set B, are elements within A union B. So this actually gives A union B. Okay, so this is done. I'm just going to clean it up because I don't really have enough space. So alright, now what is A union B complement? So again, we draw, my God, my rectangle is horrible. Alright, so we have again A and B. Now, which part is represents A union B? So let me use dots to show that. So let's say this, we know that together with the overlapping area and then all of the set B, all of this is A union B. Now, complement of that means all elements that are found within the universal set, so they are bound within the rectangle, but they are not within A union B. They are not inside any of these dotted places. Now, if you look carefully, that seems to be outside of the rectangle. So the whole entirety of this area, everything outside of A and B are A union B complements. Okay? So the shaded region is A union B complement. Alright? Okay. So I'm going to clean it up again. Shame on me. Okay, now we have this. And of course, this is the universal set. We have A and we have B. So A, B. Now again, A intersection B complements. So again, let's use dots to show A intersection B. A intersection B will be the area where A and B overlap. So that is this region. Alright. Now complement of that will be all of the elements other than that. And it can actually include everything else outside. Everything else outside. Everything else other than the overlapping region. And that gives A intersection B complement. Okay? Alright, as long as it's in the universal set, but not inside that. Alright. Oops, I meant to clean it. Okay. So now let us do. So we have another A and B right here. So this time we want to show A complement intersection B complement. A complement means not A, right? So all elements within the universal set, so they must be within this, but not in A. Now if you look at it, everything excluding A, right? So allow me to just use dots to show all that. So that will be everything excluding A. So we don't even touch the overlapping region because A still bounds that. So every single place. Sorry, I meant to put dots, not lines. That's a mistake. Okay, so this is A complement. Now, what about B complement? Everything that is not B. Okay, we can see that B is this area, right? But we are looking for everything that is not B. So meaning these dots will have to go away from B as well. So we're going to clean them. Let me change to a smaller one so I can. Alright. So we can see that everything else other than what we didn't touch. So I'm now going to shade that region. So this whole area is A complement intersection B complement. Alright, now you'll notice that this is the same as A union B. And notice oh no, I just made a mistake. Sorry about that. Okay. This area that I shaded, that is, so this area, sorry. Oops. This area that I shaded, that in fact is A union B. But the dotted region is A complement intersection B complement. So the dotted region is actually A complement intersection B complement, not this. Sorry about that. So these dots, where the dots are, that is A intersection B complement. A complement intersection B complement. So none of these elements can be found in A or B. Alright? And of course, what remains will be A union B. Now, what about A complement union B complement? A complement union B complement. Let's see how that works out. I can just clean everything. So we have, oh God, not drawn to scale. So we have A and B, all right? So A complement union B complement. Okay. So where is A complement? All right. So again, this is A. So everything that is not A, I'll use dots. So there we go. Dots, 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 all over the place. Sorry, I meant to put dots. Okay. So excluding the circle here, alright, everything else is A complement. What about B complement? Not B. So, and then we are adding like B complement too, right? So B complement, I'm going to use cross like this to represent it. Now this is B. So everything other than that is B complement. So this, all these places, and also all of these, all of that, 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 all of that. Okay, so now we're finding that A complement union B complement. So we are going to look at where we can find both dots and crosses, or dots alone or crosses alone. Wherever we can find any of these symbols, that will be this. So I'm now going to do a final shading. So all of these regions I'm shading, that is A complement union B complement, together with this. So you realize that the only unshaded region is the overlapping region. So only the overlapping region is unshaded. Everything else is shaded. And that is A complement union B complement. Okay. Alright. Now remember that this was equal to A intersection B complement. Remember, A intersection B is this part, is this region. Complement of that means everything other than that region, which is everything else out there, right? So this, if you remember, we call this De Morgan's law. So if you like, this is an illustration of that law, De Morgan's law. And you can also verify that this and this is equal. You can verify it on your own. So with this, in the next video, we'll solve a few set problems, and you can leave your questions and comments below. Don't forget to subscribe and share and like it if you like it. Otherwise, till next time.